All right, that brings us to the convergence theorem for power series. If the power series sum n equals 0 to infinity of a sub n x to the n converges at x equals c, which is not 0, then it converges absolutely for all x with the absolute value of x is less than the absolute value of c. And if the series diverges at x equals d, then it diverges for all x with the absolute value of x greater than the absolute value of d. This theorem is somewhat easier to understand. I should say the corollary is a little bit easier to understand, and that's all we're really going to use. So as a corollary to that theorem, we have the following. The convergence of the series sum c sub n times x minus a to the n is described by one of the following three cases. Number one, there is a positive number r such that the series diverges for x with the absolute value of x minus a is greater than r, but converges absolutely for x with absolute value of x minus a is less than r. The series may or may not converge at either of the endpoints x equals a minus r and x equals a plus r. Case number two, the series converges absolutely for every x. In that case, we say r is infinite. And case number three, the series converges at x equals a and diverges elsewhere. In that case, we say r equals 0. The number r is called the radius of convergence. All right, so to test a power series for convergence, and we were doing this earlier, first use the ratio test or possibly the root test to find the interval where the series converges absolutely. Ordinarily, this is an open interval. Absolute value x minus a is less than r, which means the same thing as a minus r is less than x is less than a plus r. Step two, if the interval of absolute convergence is finite, test for convergence or divergence at each endpoint, as in examples 3a and 3b, which we looked at earlier. You can use a comparison test, the integral test, or the alternating series test. Step three, if the interval of absolute convergence is a minus r is less than x is less than a plus r, the series diverges for absolute value of x minus a is greater than r. Can't even converge conditionally there because the nth term does not approach 0 for those values of x. All right, so next we will look at these three examples. First, we want to find the series radius and interval of convergence. And then for what values of x does the series converge absolutely and conditionally? All right, so switching over to the tablet. Here is the first example. So again, we're going to use the ratio test to start off with. The limit as n increases without bound of absolute value a sub n plus 1 over a sub n is going to equal the limit as n increases without bound of the absolute value x plus 5 to the n plus 1 over x plus 5 to the n. And of course, x plus 5 to the n plus 1 divided by x plus 5 to the n is just x plus 5. So we are left with the limit as n increases without bound of absolute value x plus 5. Well, as far as n is concerned, absolute value of x plus 5 is constant. So this limit is just absolute value x plus 5. All right, so remember, when we're using the ratio test, we call this limit rho, and the series converges absolutely when rho is less than 1. Okay, so this is going to answer the question in part. Well, it's going to be at least a big part of the answer. All right. So when the absolute value of x plus 5 is less than 1, the series converges absolutely. Note that that means the same thing as -1 is less than x plus 5 is less than 1, which means the same thing as -6 is less than x is less than -4. Okay. So it definitely converges absolutely for those values of x. So now we have to test the endpoints, which are -4 and -6. So I will start with -4. When x is -4, this series becomes the sum n going from 0 to infinity of -4 plus 5 to the power n, which is just 1 to the n, which is just a series of ones. So does a series of ones converge or diverge? Well, it diverges by the nth term test, for example. As n increases without bound, the limit as n increases without bound of 1 is just 1, which is not 0. All right. 1 plus 1 plus 1 plus 1 plus 1. If you keep adding up a bunch of ones, eventually you'll surpass any number you can think of. So when x is -4, the series diverges. And when x is -6, we have the sum n going from 0 to infinity of -6 plus 5 to the n. All right, so this is the sum n going from 0 to infinity of -1 to the n, which is this series, 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. And that series also diverges by the nth term test. The limit as n increases without bound of -1 to the n does not exist, right? Because it just oscillates between 1 and -1. All right, so this series, the power series, converges absolutely for x between -6 and -4. Diverges elsewhere. Okay, so one way to specify the elsewhere, just in case they ask, remember I got this inequality originally from absolute value x plus 5 is less than 1. So you could just say absolute value x plus 5 is greater than or equal to 1. Oh, and by the way, just going back here, when we first got this inequality, my radius of convergence is right here, because remember they talked about the absolute value of x minus a is less than r. Okay, now there might be some examples. Notice that you have to get the inequality in that form, all right, in order to be able to read off the radius of convergence. Okay, so I just want to note here that r equals 1. The radius of convergence is 1. I like to, of course, when you hear the word radius, you think of a circle, right? So if you picture this interval on a number line, imagine that there is I drew it too high up here to look like a circle. right? But imagine that that interval is the diameter of a circle, and then your radius is right here. Okay, so it kind of makes sense that the radius of convergence is 1. All right, next example. The sum n going from 1 to infinity of -1 to the n times 3 to the 2n times x minus 2 to the n all over 3n. All right, I have a feeling that this one might go a little quicker. So we need to, again, look at the ratio test, the limit as n increases without bound, absolute value a sub n plus 1 over a sub n. Okay, I'm going to go down here this time because I keep running out of room. All right, a sub n plus 1 is -1 to the n plus 1 times 3 to the 2 times n plus 1. Remember, you have to be careful there. Times x minus 2 to the n plus 1 all over 3 times n plus 1. All right, divided by a sub n, which means multiplied by the reciprocal. So that's going to be 3n over -1 to the n times 3 to the 2n times x minus 2 to the n. Okay, so what do we have? Well, -1 into -1 to the n plus 1 leaves a -1, and that -1 is going to disappear because of the absolute value. X minus 2 to the n into x minus 2 to the n plus 1 just leaves an x minus 2. All right, now these powers of 3, I want to be careful because the exponent on the top power of 3 right here is really 2n plus 2. So if I divide 3 to the 2n plus 2 by 3 to the 2n, I am going to be left with 3 to the 2, right? Oops. Okay. So then, what do we have? We have, well, we can ignore the -1. We have absolute value 3 squared times x minus 2 times 3n over 3 times n plus 1. All right, so a couple of these things can come out of the limit. 3 squared can come out, might as well call it 9. This x minus 2 has to stay in absolute value. And then limit as n increases without bound of three n over 3 times n plus 1. That limit is equal to 1. So we are left with 9 times the absolute value of x minus 2. This power series will converge absolutely as long as that expression is less than 1. All right, so this is a perfect example of what I was talking about earlier. If 9 times the absolute value of x minus 2 is less than 1, that means the absolute value of x minus 2 is less than 1/9. So that would be my radius of convergence. R equals 1/9. Okay, so now we have to, unfortunately, I thought this was going to go a different way. Now we have to look at the endpoints. So the endpoints of this interval, starting with absolute value x minus 2 is less than 1/9, that means the same thing as x minus 2 is between -1/9 and 1/9. And if you add 2 to everybody, that means that x is between 17 ninths and 19 ninths. All right, so we have to test x equals 19 ninths and x equals 17 ninths, unfortunately. All right, so let's see, why don't we start with 19 ninths? That is going to give us the sum n going from 1 to infinity. -1 to the n times 3 to the 2n times x minus 2 to the n. So remember, x is 19 ninths. That's going to give us a 1/9 to the n here. And that's all over 3n. Sorry, I keep switching back and forth. Hopefully I'm not making you dizzy. All right, now we can simplify this thing because remember 3 to the 2n can also be written as 9 to the n, right? So we have 9 to the n times 1/9 to the n. These two things are just going to cancel each other out. So that's going to leave us with the sum n going from 1 to infinity, -1 to the n over 3n, which is what? -1/3 plus 1/6 minus 1/9 plus 1/12, yada, yada, yada. All right, that series converges by the alternating series test. Now, one thing that's a little different about this example from the one we did earlier is they do want to know specifically, is it absolute convergence or conditional convergence? Well, this series converges conditionally. Let me show you why. Okay, so the question is absolute or conditional. Well, if you look at the sum n going from 1 to infinity of the absolute value, -1 to the n over 3n, that just gives you the sum n going from 1 to infinity of 1 over 3n. And that is just a multiple of our harmonic series. Remember the harmonic series? We know the harmonic series diverges. Okay, so that means the alternating series converges conditionally. Sum n going from 1 to infinity of -1 to the n over 3n converges conditionally. All right, and finally, we have to look at the other endpoint, x equals 17 ninths. So I'll start that down here. That's going to give us the sum n going from 1 to infinity, -1 to the n. You know what? I'm going to take this 3 to the 2n and write it as 9 to the n, because I think that'll make life simpler. Okay, now remember, the next factor was x minus 2 to the n, and now we're replacing x with 17 ninths. That's going to give us a -1/9 to the n here, and that's all over 3n. Okay, so when you multiply 9 to the n and -1/9 to the n, That's going to give you -1 to the n. Let's see, can I squeeze this all in here? So we have the original -1 to the n. And now we have multiplied these two things together, and that gives us another -1 to the n. That's all over 3n. Oh, this part is going to be simpler actually than 19/9. This much room will be plenty. All right, -1 to the n times -1 to the n is just 1, right? So that gives us the sum n going from 1 to infinity of 1 over 3n. And we already said that this series diverges. All right, so putting it all together. The original power series converges absolutely for x between 17/9 and 19/9. It converges conditionally for x equals 19/9. And everywhere else, it diverges. All right, and that is the idea behind testing a power series for convergence.